Okay, so lecture 5.1, root locus definition. We're going to start out with a section that pretty much boils down to the statement, closed loop poles are hard to find. It's a little more involved, but we are going to explore why that is the case and what gives rise to it, and what we can learn along the way will help us to mitigate this hardness. Okay. A feedback system's closed-loop poles determine its stability and transient response. These poles depend on parameters in the controller, often the gain, as shown in figure 5.1. So this is the simplest type of controller that we'll consider, which is that in the controller block of our usual feedback block diagram, we're going to have a gain, just a simple gain. So whatever the error comes in will get multiplied by a number, and that'll go out into the plant as an input. This is actually a rather effective type of controller, and if you have the right gain. So if you have the wrong gain, then it's very terribly performing. So you gotta have the right gain, but just using a gain, we can actually get controllers to perform reasonably well sometimes. And these were the original kind of controllers. You can build these with like an op amp pretty easily. Changing like the value of a resistor would change the gain of the op amp, and you can dial in your controller using that. So, and we'll talk a little bit about instantiation more in Control 2 or in Control 1 next year. If you decide to take that in the fall, it's an elective. I'm teaching it. I recommend that. We'll talk about how to actually like instantiate some of these things into hardware. For now, we're focused more on design and not as much on hardware, because this could be instantiated in all kinds of different hardware, whereas if we talk about one piece of hardware, then we've got to talk about a lot of different pieces of hardware, and they're just very specific. That kind of knowledge doesn't age well, because then like next year's models come out, and then you got to find a new way to do it. So this stuff is universal, whereas that stuff is specific to certain hardware. But we'll talk a little bit about it in Control 1. Now, and also I'll have a demo day in here, and then I'll talk about it a little bit too, because I'll have some physical hardware to show you. Now, okay. So with this gain K, we're gonna try to do some control. Okay. Now, the poles depend on parameters in the controller. So the closed loop poles depend on parameters in the controller, often in the gain K. So if we've got this feedback block diagram here, then the gain, if we look at the closed loop transfer function, R is the command, Y is the output. The gain shows up as a factor in the poles in the closed loop transfer function. We find the poles in the closed loop transfer function by setting the denominator equal to 0, right? And K's in there. Problem is, we want those poles to be in certain places to match our performance criteria, right? Like maybe the percent overshoot or the rise time or something like that we care about. And we want those poles to be in a certain location, but their location depends on gain K, and solving backwards for the gain K is quite difficult to do, especially if it's a higher order system. Okay, and solving for an expression in which we know where those poles are as a function of K, or the other way around would be even our preference, is intractable, especially for higher order systems. So let's take a look at that. So we define the forward transfer function to be the transfer function from a loop's error to its output Y. So in this one, from the error to the output Y, what's along that path? K, G, right? So that's our forward transfer function. And the reverse transfer function, or the feedback transfer function, is from y to the summation block. So in this case, it's h, right? So forward and then feedback is h. Then there's one more term that we need to make sure we keep straight, is the open loop transfer function, which goes from the error all the way around the loop to here, but it doesn't close the loop. So it's still open loop. It doesn't go through the summing junction. The closed loop transfer function is from R to Y, so we've got a closed loop here. The open loop transfer function goes K, G, H, and then stops. Doesn't go through the summing junction. So open loop transfer function is KGH, forward path transfer function is KG, and the feedback transfer function is H. That's important terminology. It's a little bit hard to keep straight sometimes. A lot of times people confuse KG, the forward transfer function, for the open loop transfer function. Open loop should also include the feedback transfer function. Yeah?
So then is the open loop useful for determining where the error is? So like
Where what is?
Like, so what the error is without adjusting for it?
It's useful analytically in the process that we're going to look at here. So we're going to start with the open loop transfer function as a sort of starting point for analyzing for a closed loop. Yeah. Because the closed loop is tricky. The closed loop transfer function is tricky. It's got k in the denominator. Yeah. So, very good. We break down g and h into numerators and denominators. So g, we'll say, is g numerator divided by g denominator, and h is h numerator divided by h denominator. So hn, hd, gn, gd. So if you plug that into the closed loop transfer function, we see where all the numerators and denominators end up, right? So we make the following observations about 5.2. The closed loop poles, which we find by setting the denominator equal to 0, right? These are the things that we're most interested in. What are the closed loop poles? They depend on k, but for controller design, k is that for which we are solving. Okay, like we want to know what k to do. That's what we're designing. We're designing this controller. We want to know what k we should have, but we can't find the poles unless we know k. We want those poles to be in a certain place. Ideally, we could just like say, okay, I want the poles in a certain place and give me the gain necessary. But it's not mathematically very feasible to do that back calculation. So, an analytic solution for the closed loop poles is intractable for systems of order greater than 3. And even with those, solving backwards for I want my poles to be here and here is also intractable because you don't know where is possible, where you can have poles. So it's really it's a tricky problem, especially when you get to poles of order higher than 3. So you think about it, if you had a second order system, so a second order polynomial, and you wanted to solve analytically for what the pole, where the closed loop poles are going to be depending on the gain k, you could do that, right? You could use a quadratic formula. You could plot him for all values of k, no problem. But you need to keep in mind that the quadratic formula, there's a cubic formula, there's maybe a quartic, and there may even be quintic? Maybe fifth order one solution, analytic solution. But these ones, even the third order one is intractably large to look at and understand where k is and how it's going to influence the pole location. And once you get higher than that, there's just no chance of understanding it. So what we typically resort to is finding, for a given value of k, using a numerical root finder, which is actually very effective. So if these are all, if k is just 1.3, then you could find out what the poles are for that k. So you can just use a numerical root finder to find the closed loop poles given a bunch of different gains, but you have to do it numerically. So that is, the closed loop poles are hard to find. Okay, you have to choose a specific value of gain k to make it easy to find it, but you want to know for all k So that's kind of a lot of calculation to do. So 2, another observation. As k goes to 0, so that means this term right here goes to 0, right? Which means this whole thing gets wiped out. The closed loop poles approach the open loop poles. So the closed loop poles then are just GD and HD. The denominators of G and H equals 0. Well, the open loop transfer function is KGH, which is just KG numerator, H numerator divided by G denominator, H denominator. And so the open loop poles are found with this formula. And now if k is 0, the closed loop poles are also found with the same formula. So that's important. As k goes to infinity, so instead of setting this to 0, it goes to infinity. If this goes to infinity, this term's going to become way bigger than this term, right? So this term will be dominated by this term, and will approach the G numerator, H numerator equal to 0, which is to say the zeros of the open loop transfer function. So as k goes to infinity, the closed loop poles approach the open loop zeros. Okay. Interesting observations, important observations. These last two give us the start and finish for closed loop pole locations when k is varied from 0 to infinity. Okay? If we think of finding the closed loop pole locations for different values of gain, if we start at 0 and we go to infinity, these last two observations tell us where we'll start and where we'll head, where we're going to go in the long run, right? In this procedure, we will now define as the root locus. Okay? So that's what the root locus is going to be. The graph of the closed loop poles for all different values of gain. Okay, from 0 to infinity. So let's jump right into the definition then. The root locus is the collection of closed loop pole locations for varying proportional controller gain k. So that's what it is, and that's key to remember. I mean, this is the same with the Bode plot. Like we're going to get into all these details of like how to construct it and all that, but what is it is the most important thing you can know about it. So it's just a collection of closed loop pole locations for varying proportional controller gain k. So you vary k from 0 to infinity, and you've got the root locus. Recall that for a feedback system with plant G and feedback transfer function H, the closed loop transfer function is this. We derived this in just the preceding section. And we also learned that finding the poles is difficult in general. However, let us consider our observations from 5.1.1. We know our starting points, which is at k equals 0, the closed loop poles are equal to the open loop poles. So that's a good start. The open loop poles don't depend on the gain, so we can just find them. And we know our endpoints. So as k goes to infinity, the closed loop poles are equal to the open loop zeros. So we also know what those are. Those also don't depend on the gain. Therefore, we can consider the root locus to be a collection of curves that begin at the open loop poles and terminate at the open loop zeros. Okay? So they give us our closed loop pole locations for all different gain values. And we know where they start and we know where they finish, and we're going to develop we're going to develop criteria in the next section here, the magnitude and phase criteria for what always has to be the case everywhere along this trajectory, everywhere along these curves. So the magnitude and phase criteria. The closed loop poles can be found by setting the denominator of the closed loop transfer function to 0 and solving for the values of S that satisfy this condition. That's the standard way of finding poles for anything, right? Any transfer function. Set the denominator to 0, solve for the values of S, those are our poles. Examining the closed loop transfer function, we see this is equivalent to, so we just wrote the closed loop transfer function right here, right? It's equivalent to saying 1 plus k g of S h of S equals 0, right? Setting this denominator equal to 0 is what we do, always to find the poles. So we can rearrange this slightly, and we can rearrange it to have magnitude. Let's see, no, we're not going to do that yet. We're just going to subtract 1 from both sides. We're going to say k g of S h of S is equal to -1, just subtracting the 1 over. Now, g and h are complex functions, and they return complex numbers. Let's think of this -1 as being, it's real, but it's part of a larger space that is complex. So we can represent it as a complex number, which is 1, has magnitude 1, and direction, the angle associated with it, is 1 plus 2m pi, where m is an integer. So m is a member of the set, the integers, which is that z with the double strike. So in other words, this is a fancy way of writing that in the complex plane, real, imaginary. The real number -1 is right here, which has magnitude 1, so length 1, and angle pi, right? Also equivalently, 3 pi, 5 pi, 7 pi, 9, 11, 13. All those pies. Okay. At my dinner party on Friday that you guys aren't invited to, my friend is making pie for that. Oh my goodness. She was sending me like this list of like the potential pies and they were so good sounding.
You're just rubbing in.
I know.
I didn't feel like I was missing out that much, and now I'm really missing out.
Yeah.
So here's the only problem. You have a LinkedIn that I found, so it might show up at your house.
Uh-oh. Well, I would
Watch out for the dog.
I would make like Jesus' disciples and deny you. Ouch. I do not know this man. Okay. So well, I'll tell you what. If this party goes well and my friend who makes the pies is down, we'll do another little soiree and have you guys come and we'll do pies. Okay.
You could do like in the 50s, where they just leave them on the windowsill with the window open.
Yeah, you gotta watch out for all those cartoon like wolves that are gonna come by and eat it.
That's me, yeah.
Yeah, that's you. Okay. Equation 5-4. Sorry, I got distracted with pi. It's an easy thing to do, so you got to be careful. So, okay, so this equation 5-4, gives rise to the magnitude and phase criteria. So, the magnitude criterion is that the root locus must everywhere satisfy the criterion that the magnitude of KGH that's a magnitude, not a parenthesis, equals 1. Okay? That's just a direct result of 5-4. For there to be, so the root locus must everywhere satisfy the criterion means wherever in the complex plane there is a closed loop pole, this must be true. Okay? So that's important. And notice what we have here. This is the open loop transfer function, isn't it? KGH. So the magnitude of the open loop transfer function multiplied by the gain, well, actually, including the gain, includes the gain, must equal 1. So that's important. Okay? We're going to use that quite a bit. The second criterion is that the root locus must everywhere satisfy. So the root locus must everywhere satisfy the criterion. This one is the phase criterion, so we're going to look at the phase of KGH, the open loop transfer function, must be equal to 1 plus 2m pi and 2 pi additions thereof, for m being an integer. So that gives us 2 criteria, right? Great. So these criteria are always satisfied, and so they will be our guide to understanding, sketching, and designing with the root locus. So what follows in lecture 5.2 is going to be a set of rules for constructing where the root locus is in the complex plane, and our rules that we'll develop all derive from the magnitude and phase criteria, which themselves are derived from just this simple equation 5.4. Now, before we proceed, what about negative gains and positive feedback? So we typically consider only non-negative gains for the root locus, since negative gains typically lead to instability. However, this is only true for systems with positive open loop transfer functions. So if your open loop transfer function is negative, for whatever reason, then this is what we have to do. So when encountering a negative open loop transfer function, it is advisable to temporarily treat it as positive, proceed with the controller design, then multiply the controller by -1, or use positive feedback. Either one of those will result in a controller design that is good or reasonable. So that's the method of mitigating that situation. So, but if one suspects a negative gain might be of service in a specific controller, because often slightly negative gains can remain stable, so you can go to negative gains, but usually, eventually it goes unstable, so we kind of just lop that off usually. Or if one is building an unstable system intentionally, develop the root locus for negative gains, or equivalently, for positive feedback. For these occasions, see the Nice textbook. So what we're going to do in lecture 5.2 is we're going to develop all these rules for assuming positive gain, okay? Now, there are similar rules for negative gain, but they're all like flipped. Okay, it's like the reverse of all of these rules. And I don't encourage you to learn the negative gain rules because it's hard to keep the positive ones straight then if you learn the negative ones and the positive ones. So just learn the positive ones and know that if you have need of doing negative gains, then that there is a technique that's described in the Nice textbook. I would actually encourage you to use MATLAB instead. MATLAB will draw the root locus diagram for you. So doing root locus construction by hand, I think only do that for positive gains. Don't worry about the negative gain, developing any intuition for that, because I think it'll just confuse you. But, I mean, if you are really good at keeping things straight in your memory, maybe you can do it. It's fine. It's not particularly useful to do the negative gain one. But okay. So stick to positive gains and tip your bartenders. You know, those are the rules that I like to live by. Okay. All right. Any questions on this, the definition of the root locus or anything?